Okay, so one of the first things that you likely remember from your GCSE are the terms AR for relative atomic mass. Okay, so that's relative atomic mass. And then we have MR for relative formula mass. Now, a lot of students get a little bit confused about when to use each one of these terms, and it's a lot simpler than you think. AR is when we're referring to one singular element. So, for example, lithium has an AR of 6.9 grams per mole, as you can see here, its relative atomic mass. Okay, and that means if I had 1 mole, which remember is Avogadro's number of particles, so 6.02 times 10 to the 23 particles of lithium, so it would be atoms in this case, then it would weigh 6.9 grams. Okay, so 1 mole weighs 6.9 grams, 2 moles would weigh 13.8 grams, and so on and so forth. So per mole, 6.9 grams for lithium. Let's do the same for calcium quickly. Its AR for calcium would be 40.1 grams in a mole. You'll notice as well that I'm now writing these to 1 decimal place, as that is the standard in A-level chemistry. Even if that number is a 0, you still need to write these to 1 decimal place. Now, MR is whenever we're looking at a formula. So say, for example, I was to be looking at lithium chloride. Okay, so LiCl. Well, now that's a formula because it contains more than 1 atom. Okay, this one in particular does just contain more than 1 element as well, but we could also be talking about a formula like O2, where it's still only 1 element, but it's more than 1 atom. Okay, so anything with an actual formula, then we're going to be doing relative formula mass. So let's have a look at lithium chloride quickly. Well, lithium weighs 6.9 grams in a mole, and chlorine is 35.5 grams in a mole. And if we added those two together, then we would get 42.4 grams per mole. Okay. And then with oxygen, each oxygen is 16 grams per mole as its AR, but we've got 2 of them. So that's 16.0 times 2, and that will give you 32.0 grams per mole as the relative formula mass for oxygen. Now you can see I've kind of skipped between 2 different formats here because my target audience, you're used to grams per mole as our unit being written G/mole, but at A level we do actually write that G times mole to the -1. So that's our new way of writing the units for either relative atomic mass or relative formula mass. So now what you can see is on the left here, I've written some chemical formulae for you. Aluminium chloride, iron oxide, and magnesium hydroxide. And I'd like you to apply the method that I just showed you for calculating MR to calculate the relative formula mass for each one of these compounds. If you do pause the video, use the periodic table I've drawn on the right here. And there's a link in the description to this exact periodic table as well, so you can have your own copy downloaded and printed out for this video. And then do those calculations. Then come back to the video and we can see if you got your answers correct. Okay then, so our first one was this aluminium chloride here. So you should have got aluminium as having a relative atomic mass of 27.0. And then we've got 3 chlorines, each at 35.5. So I'm going to do that 35.5 multiplied by 3. I'm going to add all of that up and we'll see what we get. We should have got 133.5 grams in a mole. Okay, so grams per mole like that. Okay, the next one then, iron, we've got 2 of them here. Iron weighs 55.8 according to my periodic table. So we've got 55.8 multiplied by 2. Okay, and we're going to add that to the oxygen, each oxygen at 16.0 as seen over here. So we're going to do 16.0 multiplied by 3. We'll add all that up and see what we get. And you should have got for that one 159.6 grams per mole. Okay, next up we've got magnesium hydroxide. Well, it only contains 1 magnesium here at 24.3 grams in a mole. And then looking at these brackets here, this is important. Inside the brackets, you've got 1 oxygen and 1 hydrogen. However, the brackets have been multiplied by 2. So that means everything inside the brackets, whatever numbers currently apply to it, you need to multiply by 2. So that's in fact 2 oxygens and 2 hydrogens. So we're going to add that to 16.0 for the oxygen multiplied by 2. And we're going to do 1.0 for the hydrogen also multiplied by 2. Add all that up and see what we get. And you should have got for that one 58.3 grams per mole. There we go. So that's a little bit of the strategy there for working with formulae that include brackets. We looked at those with brackets and compound ions in lesson 1. So if you haven't seen my AS transition lesson 1 yet, please do go back and take a look at that and do the tasks first, because that will enable better understanding of formulae that include brackets like this one here. Okay, now let's look at how we could apply this to some equations. Okay, so this is a really common reaction that you should have during your GCSE come across before. This is the reduction of iron oxide using carbon to extract iron. It's a classic example of a displacement reaction. It's also redox because one element is oxidized and the other is reduced. What we've got here is iron oxide, and that's the form in which iron ore comes. That's the main compound in iron ore that we get most of the world's iron from. So it's got the formula there, Fe2O3. And if we react this with carbon inside a blast furnace, then what's going to happen is the iron's going to be displaced because carbon is more reactive than iron. So the carbon here will pair up with the oxygen to go and make CO2, and that will displace the iron to make pure iron there. Now, you're quite often asked a question on this equation, and it will be something like, if I want to make a certain mass of iron, how much iron oxide do I need to put into the blast furnace? It could be, if I have this much iron oxide, how much carbon do I need to react it with? Or it could be, if I want to make this much iron, how much iron oxide do I need? Or how much iron oxide do I need to make this much iron? And the method I'm about to teach you will enable you to answer any single one of those questions. And we're going to use something called the grid method, or the column method as it's sometimes known, in order to do any calculations really related to this equation. So let's say, for example, the question says this. If you have, let's say, 100 grams iron oxide, what mass of iron, oops, wrong button, iron, is produced? Okay, there we go. So simple question there. Our numbers might not be great, but we're going to see what happens. Okay, so first of all, we know that we have 100 grams of iron oxide. So we know something about this one here. And we're being asked about iron. So this is the one that we want to try and find something out about. So what I always recommend to my students is the first thing you need to do is rewrite the equation. So we're going to do that now. 2Fe2O3 plus 3C goes to form 4Fe plus 3CO2. And then what we're going to do is draw some columns. So I'm going to draw a column on anywhere where there's a plus or an arrow, like that. Not perfect straight lines, but that'll do. And then I'm going to write 3 terms on the left-hand side. Mass, and that has to be in grams. MR, has to be in grams per mole. And mole, which is in mole. Okay, and then we're going to write in any information that we know or we can work out. So we were interested in these two, so anything else we can ignore. We know the mass of iron oxide is 100 grams. Then what we're going to have to do is work out its MR. Now it's very, very important that in this MR row, you never multiply the MR at all by the coefficient. You must not do that. Some teachers teach it that way at GCSE as a trick to make calculating reacting masses more accessible to a vast majority of students. However, if you've been taught that way at GCSE, it will really disadvantage you at A level if you then try and apply it at A level. So very, very important that this MR is solely for the formula that is there and is never for the coefficient. You need to ignore the coefficient when writing MRs down. Okay, so we've got 2 ions, and if I remember rightly, sorry, I just move over to my other screen so I can get my periodic table back up. Iron weighed 55.8, and we've got 2 of them. So we're going to have to work this out quick. So that's 2 times 55.8. And we're going to add that to our 3 oxygens, each at 16.0. So let's work out what that MR was quickly. Okay, so I've typed that into my calculator and I've got 159.6 grams per mole. Now, just to tidy that up a little bit, I am going to get rid of this working, and then that way we've got some nice clean numbers to work with here. So now, hopefully you remember that the equation that we use in order to calculate moles of a substance, well, the base equation that you probably remember is mass equals Mr. Mole, or mass equals MR times mole. Okay, so if we're rearranging that for mole, then we should be using the equation mole equals mass divided by MR. And in this particular example, that gives us the sum of 100 grams divided by 159.6 grams in a mole. Okay, so grams over grams per mole. So those grams are going to cancel out, and you're effectively doing 1 over mole to the -1, so the -1 cancels out, and you will get an answer that is in moles. So let's find out what that answer is quickly. Okay, so on my calculator, I've got the answer of 0.627 when I've rounded it. So I'm just going to get rid of that working quick. Obviously, you'd leave all of that working in an exam. They would need to see all of these calculations to see what you've done. So I've got 0.627 moles here of the iron oxide. Now, a minute ago, I told you to ignore the coefficient, and that's true for the MR. But the coefficient is particularly important for the moles. Okay, so we do have to apply that coefficient when we're working with moles. So this mole value here will follow the ratio of coefficients in the equation. So hypothetically, imagine this number was 1. Okay, then if this number here was 1, then this number over here would be 1.5, because the ratio of iron oxide to carbon is 2 to 3, which is the same as 1 to 1.5. So if this number was 1 here, it would be 1.5 here, it would be 2 here, and it would be 1.5 here. So the mole the mole row going across like this has to follow the same ratio that you see via the coefficients in the equation. So we reserve those coefficients for setting the ratio of the mole values in this row here. But I haven't got a nice integer here, whole number. I'm working with a decimal. So it's important that now what I do is I divide this number by the coefficient in its own column, and then multiply the answer to that by the coefficient that I've got in the target column I'm trying to get to. And in this case, that's iron, because the question was only about iron oxide and iron. It didn't care much for carbon and carbon dioxide. So what I'm going to do now is transfer this mole value across, grab my pen again. So I'm going to take this number, and I'm going to first divide it by the coefficient in its own column. So that's a 2. So I'm going to divide by 2. And then I'm going to multiply by the coefficient in the column that I'm trying to get to. So then I'm going to times by 4. Now, dividing by 2 and then timesing by 4 arguably is just the same as timesing by 2, right? But I teach it in this sort of really fundamental way, such that if you haven't got numbers that easily fit into one another like we've got here, then that method is easily transferable. So 0.627 divided by 2 times by 4. That will give me an answer of 1.253 as the number of moles of iron that we will get from 0.627 moles of iron oxide. Now that makes sense because actually you've got 2 ions per iron oxide here. So we're going to get twice as many ions, as it were, twice as many ions than you would have in the original iron oxide. So now what we've got to do is we're trying to get this mass number here in this column. But in order to do that, we're going to need an MR value for the iron. Now, with this MR value, remember, it's not going to use this coefficient here. You're not going to use this. You're simply going to use the formula you're given for the MR. And the iron, if I remember rightly, let's just double check, was 55.8 grams per mole. So that's not really an MR, it's more of an AR, but it can go in that column. So 55.8 grams in a mole. Okay, so just for the formula, not using the coefficient, the only row that uses the coefficients is this mole row. Okay, so now what I've got to do is calculate a mass. So I'm going to have to go back to my equation and use it in this rearrangement here. So mass equals MR times mole. So I'll just ignore this over here quickly because I don't care much for it. So my mass here that I'm calculating is going to equal my MR, which is 55.8, multiplied by my moles, which is 1.253 moles. And let's type that in quickly. So times that by 55.8. I left the number in my calculator ready to use. So there we go. I've got an answer. And the answer is 69.925 grams. And there we go. We've calculated now the mass of iron that can be extracted from a given mass of iron oxide. So now what we're going to do is turn this on its head a little bit. I'm going to give you a target mass of iron, and we're going to calculate how much iron oxide would be needed to make that much iron. Okay, so let's imagine the question in this one, so we'll call this question 2, is asking you to produce, let's say, 50 kilograms of iron. So the question would be something like this. How much iron oxide would you need, or would be needed to produce, let's say, 50 kilograms of iron? Okay. And just to be clear on this, before we move on, there are 1,000 grams per kilogram. So therefore, actually, we're talking about 50,000 grams. Okay. Now, when you're doing reacting mass calculations, the standard unit that chemists use is grams. So you could do that conversion and then do all of your calculations. And then convert your answer back into kilograms. But if you want to give an answer in kilograms, let's say how much iron oxide in kilograms would be needed, then using this method, there really is no need to do that conversion. It would work without you doing any conversions of kilograms to grams. So I'm actually going to stay in the kilogram format here, despite the fact that's kind of breaking the rules a little bit. So let's write out that equation again. 2Fe2O3 plus 3 carbons goes to make 4Fe plus 3 CO2. Now, we know how much iron we want to produce, but we don't know how much iron oxide is needed. So I'm going to do my columns again. Terrible columns. Right, mass, MR, and mole. Okay then. So we want to make 50 kilograms of iron. So I'm just going to put 50 there. Okay. The MR of that iron, it's amazing that I keep forgetting, but I am actually recording these in chunks. So it's not the time you think it is. It's not all continuous. Amazing. Right. So iron is 55.8 grams per mole. Remember, ignoring that coefficient, only the mole row abides by the coefficients ratio in the equation. Coefficient, remember, is the balancing numbers. So I need to calculate this mole value here. Now my standard equation is mass equals Mr. Mole, mR times mole. So to get moles, I'm going to do mass over mR. And in this particular calculation, that means I'm going to do 50 divided by 55.8. So I'll look to the right to pause it, calculate it, and be back in a sec. Okay, and I've got an answer here of 0.896 moles. In reality, that would be kilomoles, or 1,000 times that answer, but we're really not all that bothered because we're going to give our answer in kilograms too. So now we've got a mole value, we need to follow the ratio of these coefficients here. So remember, what you're going to do here is you're going to divide your mole value by the coefficient in its own column and then multiply by the coefficient in the target column. So to get this mole value over here, to work out how many moles of iron oxide I would need, so I can calculate its mass later on, I'm going to first divide it by 4 and then I'm going to multiply it by 2. So I'm going to write left to right still because that's the way we would do the sum, but I'm going to divide by 4 and then multiply by 2. Okay, so essentially I'm going to halve it, aren't I? All right, so let's do that now. So divide by 4, multiply by 2, and I get an answer here for the mole value, technically in kilomoles, 0.448. Okay, so now in order to get this mass for the iron oxide, I'm going to need to know the MR for the iron oxide, which I calculated previously but can't remember, so I'm going to quickly redo that. Okay, so the MR of that iron oxide was 159.6 grams per mole. And remember that that MR is ignoring the coefficient. That is the true MR of just the formula you see in front of you. I keep emphasizing this because no matter how long and many times I go on about it, students do still regularly make that mistake. So now what we've got to do in order to calculate the mass is use this original rearrangement of the equation here. So I'm going to do MR times mole, so I'll just show that round here. 150, oh sorry, that should be 159.6, shouldn't it? Apologies. So it's going to be 159.6 multiplied by 0.448, and let's do that now. And I've got the answer of 71.501 grams, or kilograms, remember, because we started in kilograms, so we'll end up with kilograms, both lowercase in kilograms. Okay, so 71.501. So hopefully now you can see that this column or grid method is really, really useful for tracking the key information we need. And whenever there's a gap in a column, we can think about exactly what step I need to do next, because we really need 3 bits of data in a column for it to be complete, or 2 bits of data so you can transfer data across between columns. So this helps you think about that method in a lot more detail. So what we're going to do on the next slide is I'm going to give you a range of different calculations to do, and then I'm going to work through each one of those individually. And if you can do those, then you've mastered the skill of reacting masses. Right then, so in this first one that you're going to do yourselves, we have aluminium oxide here being produced from aluminium reacting with an excess of oxygen. So there's going to be more than enough oxygen to complete the reaction, but you're not concerned about its mass or its volume or anything like that right now. So what you're told in this question is that you've got 81 grams of aluminium, so you know something about this one, but you need to calculate how much aluminium oxide that would produce. So try to follow the method that I've described and then come back to this video and see if you got the right answer. Okay then, so what I've done here is laid out my columns and written mass, Mr. and mole on the left hand side, and I've also written in there already for you these MRs. So aluminium, a singular atom, would have a singular mole MR of 27, and aluminium oxide 102 you should have got for that one. So let's now start putting in our data for these. So we've got 81 grams of the aluminium. So the first thing we can do with that aluminium is calculate the number of moles. So remember that mole equals mass over mR. So therefore we're going to do the sum of 81 divided by 27, and you should have got an answer of 3 moles. So we'll pop that there. Then what we're going to need to do is work out the moles of aluminium oxide, which are tied to the moles of aluminium through the ratio of the equation, which we can see is 4 to 2. So what I'm going to do with this number to take it across is first divide it by the number in its own column, which is a 4, and then we're going to multiply that by a 2. So dividing 3 by 4 and then multiplying by 2, that will give you an answer of 1.5. So we've got 1.5 moles of the aluminium oxide being produced there. And then finally, we need to calculate the mass of this aluminium oxide here. So remember that mass equals mR times mole. And in this case, that's the same as doing 102.0 grams per mole multiplied by 1.5. So just do that now. And you should have got a mass of 153 grams as your final answer for that one. Cool. Let's have a look at question 2. Okay, so your next one then, we've got to look at what mass of aluminium would be required to produce 4,077 grams of aluminium iodide. We're given an equation here, 2Al plus 3I2 goes to form 2AlI3. If you're wondering why that's the formula of aluminium iodide, aluminium is a group 3 metal, 3 plus charge. Iodide is a group 7 halide ion, so it forms a -1 charge, so you need 3 of them to cancel out the aluminium's charge there. I've given you some relative atomic masses over here to work with, so if you want to pause the video here, do your calculation and see what you came out with. Right then, so to begin with, we know something about the aluminium iodide. We know that the mass of it we are asked to produce is 4,077 grams. We could have also worked out its MR, and you should have got 407.7 grams per mole, and therefore we can work out its moles. So to work out the number of moles, we're going to do mass divided by mR equals mole, and that should give you, well, 4,077. You can see I've done a nice easy one here, over 407.7 should give you 10 moles. Okay, so I'm going to put that there, 10. Then we're going to take this mole number across to the aluminium, and as always we divide by the coefficient in our own column and we multiply by the coefficient in the target column. So dividing by 2 and then timesing by 2, well, that cancels out. So this number here is just 1 to 1 with it, it's 10. The MR of aluminium that you should have got would have been 27. And therefore to work out the mass, we do MR times mole. And effectively what we're doing here is 27 times 10. So you should have got 270 grams. Okay, so 270 grams as being your answer there. Okay, so this concludes this short video on calculating reacting masses. It is an essential skill for A-level. In the next lesson, we're going to be applying this skill to titration calculations using N equals CV, or the concentration equation. So I hope you'll join me for that. It'll be especially important if you've studied combined science this year to understand concentration in the way that triple science students will have studied it before. So make sure you have a look at that video when it gets posted. Thanks very much.